I'm Antonio Sala, and in this video we are going to further discuss relationships between concepts on marginal, conditional, joint probabilities and Bayesian posterior probabilities with the roaring tiger case study we started in previous videos. We have this tiger world in which at the moment I close this central gate, tiger may be left or right with some prior probability, and when the tiger is in left or right cage, when tiger roars, it's heard in one of those doors. Maybe if it's roaring towards the passageway, let's say, then roaring noise is heard at the wrong side. The model of our problem started with a conditional probability table in which rows denote observations and columns denote tiger location, and the condition is in the columns. So we have this table, for instance, in which, when tiger is at the right-hand side cage, then 10% of the time roaring is heard at the left side, etc. And adding a missing piece of data, which is the prior probability of tiger being left or right, we'll define B as the probability of being right, so 1 minus B is the probability of being left. Then, based on this formula, we can compute the joint probability table, and in this case, joint probability tables, if I believe that, let's say, 60% of times tiger is at the right-hand side because there are, food remnants or whatever at that side, then this is the joint probability table. The elements add 1 in joint probability tables, whereas in the previous conditional table, it was the sum of the columns which added 1. If we added the rows or columns of the joint table, then we had the so-called marginal probability distribution. If I add the columns, I get 0.4, 0.6, which is in accordance with B equal 0.6, which I used to generate this table, of course. But the interesting one is the sum of rows, which tell me the likelihood of hearing noises at the left or hearing noises at the right. We see that there is a little more likelihood of hearing noises at the right-hand side door. We'll later use different values of the prior probability of the tiger being left or right, so we're going to plot the marginals as a function of B to better understand the meaning. And the marginals of the observations, here left, here right, will be adding these rows of the joint probability table. So let's do it with MATLAB code. Here we have it. This first term in the summation is the joint probability of here left and tiger right. But okay, I am directly using the conditionals and prior probability when closing the gate because those were the initial data I started the problem with. And this term here is the joint probability of hearing left and tiger left, which is the conditional times the probability of the condition, which is tiger left 1 minus B. So, as I can only hear left if tiger is right or tiger is left, then the sum of these two probabilities gives me an expression linear in B, which is the probability of hearing noises at the left door given my prior B. Of course, if I replace B equal to 0.6, I would get the marginals we saw a minute ago. Likewise, this line will compute the sum of the probabilities of here right and tiger right event plus here right and tiger left event, and then this will be the marginal probability of hearing some roaring noise at the left hand side door. And as a curiosity, we can compute the marginal probabilities with a matrix operation in which I multiply the matrix of conditional probabilities times the column vector with the probabilities of each of the conditions. Then the matrix product formula, if expanded, gives me the exact same summations we had above. So we can compute the marginals in just one line of MATLAB code. This is elegant and maybe useful if I had a lot more possible observations or tiger location states. Let us plot these functions in order to better understand what they mean. I'll use this code, and this is the plot in which the abscissa represents the value of my initial belief on where the tiger will be at the right, prior probability, and depending on that b, I will get the marginal of hearing left or right. For instance, the numbers we obtained a couple of minutes ago were those for b equal 0.6. But in general, for any value of b, we have these linear expressions that the important thing is realizing what the extreme points at 0, 1 are. Indeed, for instance, if b is 1, if I am sure that tiger is at the right hand side cage, then this number is 0.9, which was the conditional probability of here right given tiger right. Of course, if I am sure that the condition holds with probability 1, then the conditional probability is no longer a conditional. If the condition holds, it is upgraded to a full probability. So this 0.9 will be the marginal when I am sure that tiger is at the right cage. And of course, conditional and marginal in that case coincide, because the condition holds with probability 1 and the other condition holds with probability 0. Likewise, of course, this number is 0.1, which was this conditional probability in my initial setup of the conditional table. You can check that these 0.8 and 0.2 are the original numbers in the conditional table, condition to tiger left, and okay, if I am in here, probability of being at the right hand side cage is 0, so it will be at the left cage with 100% probability, so conditional probabilities upgrade to probabilities. And then for intermediate beliefs, the marginal probability is a sort of interpolation, linear interpolation, between the extreme probabilities, which are the conditionals. So with this, we better understand the relationship between marginal and conditional probabilities. The next thing to analyze will be Bayesian inference, recovering two conditionals from the joint and analyzing the Bayes formula as follows. If we have this joint probability, then if we divide each column by its sum, then we get the conditional probability table, dividing each element by the marginal. But okay, I will not do this computation on columns because then I would just recover the data I already had at start. But it's the other operation in rows, dividing each element by a row sum, which is the marginal of here left, here right. Because that new conditional table is something that I didn't have in my original data. So these four numbers are, let's say, this one will be the probability of tiger left conditioned to hearing left, and this one, the probability of tiger right conditioned to hearing left, and of course in this case rows at 1. And also the evaluation of this conditionals is called Bayes formula, Bayesian inference, so we'll discuss it in more depth just now. So let us compute the conditional probabilities of tiger right if I here left. Of course, I will compute only tiger right because tiger left will be 1 minus the stuff. Then the definition is, joint divided by marginal, or, the element of the joint probability divided by the sum of the row of the joint probability. This is how we did it in the MATLAB code 1 minute ago. But okay, if I stated my problem with the other conditional table, because I conceptually divided my problem in determining one probability of tiger being left or right when the central gate is closed, and then a second step with a conditional of hearing the roaring depending condition on which gate the tiger is, then okay, then the second expression is mathematically equivalent to the first one, but okay, it's expressed with the data I used to build my statistical model. I name this number b, and this of course will be 1 minus b, because, well, probability of hearing left and tiger right will be the conditional times the probability of the condition, and likewise the denominator, each of the two terms in the summation, will be these ones. This conditional to tiger right times the probability of tiger right plus the conditional to tiger left times the probability of tiger left. So this conditional probability expression is called Bayes formula, and then this is the conditional probability of tiger right conditioned to here left, which I obtained by manipulating the rows of the joint table. However, apart from conditional probability, this also receives the name of posterior probability, if I think in this formula being applied after actually listening to a roar on the left-hand side door. Because indeed, if the condition holds, then the conditional probability is upgraded to a normal probability. Then B is called the prior probability, the probability I had before listening to the roaring, and this thing is called the posterior probability if I apply this formula after actually listening noises in the left-hand side door. I mean, it's the same, depending on whether you think it's a manipulation with probability tables and then you call it conditional, or if it is something that you are going to execute in an application and you call it posterior probability. Okay, let us write that in MATLAB. This is the numerator of Bayes' formula, and well, the denominator, I can write it explicitly, or, well, as the denominator is the marginal, I already gave a name for that sum a few lines of code above this, which was the marginal, so, well, we get this number depending on the prior probability b. If I replace 0.6, then I would obtain the numbers in my probability tables above. The formula will output this number if b was 0.6. And this thing will be just what we need to add 1. And to have the complete table, then I need the formula of the posterior probability of tiger right when hearing right, so I will obtain this number, and then this rows will add 1. So which is the formula for this? Well, it's just changing here left by here right and applying the same reasoning. You can just pause and think, or download the PDF and the code with a link in the description. And this is how I program it in MATLAB. This is the numerator, and denominator is the marginal of here right. So I get this formula. The result is a symbolic expression function of b. And if I execute for some prior beliefs, let's say, well, if my prior was non-informative, no preference for which side the tiger could be, then if I here left and I apply the formula, then my belief of being at the right will diminish from 0.5 to 0.11. And of course, my belief on being it at the left will increase from 0.5 to 0.89. And if I hear noise at the right-hand side door, then my belief of being right will increase from 0.5 to 0.82. And of course, posterior belief on being left will decrease accordingly. Must add 1 with this. If I were almost sure that tiger was at the right side, then if I hear left 98% to 86%, but if I hear right, it will increase from 98 to 996, let's say, so you further confirm that. And well, you can just put whichever numbers you wish. In fact, we'll put all numbers in a plot in a minute. And the important thing is that, for instance, if I am fully certain that tiger is at the left-hand side, then noisy observations will not change my belief. If I am sure tiger is at the left, whatever I hear, left or right, I will still be sure that tiger is at the left. Because, maybe I have a camera and I watched it. If we represent this formula graphically with this fplot command, then the horizontal axis is the prior probability before listening to the roaring, and the vertical ordinate line is the posterior probability if I apply the formulas after hearing noises at the left door or at the right door. If I hear the tiger roaring at the right-hand side door, then I get the red plot. The posterior probability of being at the right cage increases. The 45-degree lines would mean posterior probability equal to prior probability, but okay, that only happens at the certainly sure 0 or 1 points. So red line increases my estimation of being it at the right hand side cage when I hear right, and the blue line indicates that my belief on tiger being at the left cage is increased, belief at the right is decreased, if I listen to roarings at the left door. For better understanding, let us now change the probability table to exact observations except 1 in 1,000. If tiger is left, it roars left every time except 1 in 1,000, and also at the right. Then we get this much larger increase in evidence towards the right or left side. If I listen tiger roaring right, then I am 99 point a lot things sure that tiger is at the right. Only 1 in 1,000, it may be wrong. So unless I am basically sure the tiger is left, I will conclude that tiger is right if I listen roaring at the right door. And same for left. Of course, this is in accordance to what our intuition with not noisy observations would expect. And as a last check, if when tiger is left, observations are noisy and it looks at the passageway a lot of times and I hear roaring at the wrong side 45% of times, but that does not happen when tiger is right, because maybe there is some food just behind the door. Well, in that case, Bayes' formula tells me that if I hear tiger roaring at the right, I am not sure on what's happening, because when tiger is left, it also roars a lot of times at the wrong side. But if I hear roaring at the left blue line, then I am very sure that tiger is at the left. Why? Because if tiger is at the right, I would listen left noises only 1 in 1,000. So if I hear noises at the left too, I will have a large likelihood that indeed tiger is at the left. So you know, the right conditional was very precise, but then it is listening to the left, the thing that gives me more information. Observing a very infrequent event gives me a lot of information. Well, we finished the video here. Okay, in this video we reviewed the meaning of joint, marginals and conditionals, and did some marginal plots, and we presented Bayes' formula and did put some examples, numerical ones and these graphical ones. So we finish now. Thanks for watching.